inverse functions. Now, inverse functions, when my brain hears that, I think about inverse operations. I don't know about you. So when I think of the word inverse in math, I'm thinking about like the opposite of addition, what is the opposite of addition? Subtraction. And then I'm thinking about the opposite of multiplication, which is what? Division. And then we just learned this one. I'm thinking of like the opposite of square rooting something, which is what? Squaring it. So that's the right idea. Now those are inverse operations. Now we want inverse functions. Since inverse operations undo each other or are opposites, inverse functions are also just opposites. They will undo each other, the same way multiplication undoes division and addition undoes subtraction. The way that we do this is that we switch where x and y are in the equation. If we just flip-flop where they go, it'll look super weird because normally we have equations that say y equals blah, 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 and now they're going to say x equals something, and it looks weird, but I promise we'll make it look nice afterwards. And we resolve the equation for y so that we have an inverse function. The graph of an inverse function, this is important, is a reflection of the original function over the diagonal line y equal to x. So reflections, we've normally flipped them over the x and y axis, like flipping like this up and down, side to side. Now they're going to flip on a diagonal, which looks kind of weird, I will tell you that. When we write inverse functions, it has an interesting notation. The notation you're going to use to indicate that something is an inverse is the f for function with an exponent of -1. Now, a lot of you have politely ignored the fact that I've always written my f's like this. This is the correct way in math to write f indicating function as opposed to a variable. So if you want to start making it squiggly like mine, that is truly the more accurate way to write f of x or f inverse, which is what this is called. You would pronounce this f inverse. That's how you say it. Not f to the -1, it's called f inverse, which is weird. So let's take a look at an example of a set of inverse functions. So the blue function on my screen, I know they're black and white on your piece of paper, but the blue function on my screen is the original function. It's a linear function. I know it's linear because it has a slope and it has a y-intercept. Okay, if you look at the graph, the blue function is linear. It has a slope of 2 and it crosses the y-axis at 3. These are all things that we know just because we've studied linear functions before. But if you notice, when we go to its inverse, the first thing I want you to notice is that the x and y values have switched spots. In the first one, we have the coordinate point -2, -1. In its inverse, you just flip-flop that. -1, -2. Do we see that? X and y have just switched spots. That's perfect. That's a really easy way to graph inverse functions is you just go boop, and you switch the x and y for every single thing. Additionally, the formula itself looks a little funky. What are some things you notice about this formula? Comparing it to the blue one. Maybe look specifically here and here. What do you notice? Yeah, aren't those inverse operations? Okay, good note. And what about this? What's normally happening when you have 2x? What operation? Multiplication. And look what you have with the 2 this time. Is it still multiplied? What is it now? So we're using inverse operations to create inverse functions. That's going to be what we do. Now, when we have this inverse function, it has an opposite everything. The blue function had a y-intercept at 3, which means the red function has an x-intercept at 3. We switched the x and y. This diagonal line here is the diagonal line that it will be flipped over. And if we were to fold your paper on that dashed line, y equal x, the two lines would land right on top of each other. That's called a reflection over the line y equal x. So it's reflecting over the diagonal line. And before we really get into much more about inverse operations or inverse functions, because we will be solving for them, we have to know what types of functions have inverses, because not all of them have inverses. To do this, we're going to bust out our handy-dandy horizontal line test. Now, in Algebra 1 and in 8th grade, you used a vertical line test to do something. Does anyone remember what you did with the vertical line test? More than once, right? Yeah. So we used a vertical line test before to decide if a relation or a picture was a function, because it can't repeat vertical x's for it to be a function. The horizontal line test is the same idea except the other direction. The inverse of a function is also a function if and only if no horizontal line intersects the graph of f more than once. Meaning, the same way we did the vertical line test, we take that vertical line, we just turn it sideways, and we test a function to decide if it would have an inverse. So in this first example, the function itself is blue. So if you want to highlight the actual function for yourself, since I know yours are in black and white. So this little squiggly, it's called a cubic function. We've studied it a little bit before. That cubic function, if we were to take this red vertical line and move it all the way up and down the graph, would it ever cross the graph more than once? No, so it passes the horizontal line test. So we would say that yes, the inverse of this function is a function, or it has an inverse. The inverse is a function. That's good, we want that to happen. If we do the HLT and it's a no, then that means we cannot find its inverse unless we do something weird to it. So if you look at the second example here, again, because mine is in color, it's a little easy to see. The function we're looking at is this parabola, the quadratic. It's pretty obvious what's going to happen here. How many times does this horizontal line cross the quadratic? Twice. Now, automatically that's a problem, so it fails the horizontal line test, which means that the inverse of this function is not a function. And so we cannot find the inverse unless we do something weird. And I will teach you what that weird thing is here in a little bit, but its inverse is not a function. Do we understand the HLT? HLT just tries to help us determine if the inverse is a function. Nothing about the actual function itself, but about its inverse. So once we decide it will have an inverse by employing the HLT, which we'll have to do, we're going to go on the inside, we're actually going to find the inverse. There are 5 steps to do this, 5 steps to finding the inverse algebraically. First step is like pre-step. I don't even consider it a step in my real mind, but it just literally is changing f of x to y. Because f of x and y are the same thing, and we like to switch the x and the y, so we're going to always do that first just to make it easier on ourselves. The second thing we're going to do is, without changing anything else, we are just going to change the locations of all of the x's and y's. Every x becomes a y, and every y becomes an x. Don't do anything extra. Then we're going to solve for y. Now, we've been solving for y for a while. It's just using inverse operations. For step 4, it says to restrict the domain and range if needed. This is going to be needed when we have what are called even powers. Meaning if you have something squared or to the 4th power or to the 6th power, we're going to have to do this step. Otherwise, we can basically forget about it because odd powers will be fine. And the last thing we're going to do is check our work by looking at a graph to make sure it actually does reflect over that diagonal line y equal to x. Okay. First things first, determine if the inverse is a function and then find the inverse function. Now again, might be kind of hard for you to see this because of the way it prints on your paper, but this right here is my function. We'll call that f of x. Now if we use the horizontal line test on f of x, Does it pass or does it fail? So the way you do this is you take your pencil, you put it horizontal, you move it up and down the graph, and if it never crosses f of x more than once at a time, then it passes. It passes. Okay, good. So if it passes the HLT, then we're good to go. We don't have to do anything weird. Fabulous. We keep going. My next step says to switch f of x with what? Step number 1. Replace f of x with y. So I'm just going to rewrite this to where f of x is y and literally do nothing else. Check. Easy step. My second step says to switch x and y. So literally just every time there was a y, you're going to put an x. And everywhere there was an x, you're going to put a y. Do we follow? Switch them up. At this point, we're looking at an equation that says x equals. We don't normally do that. We like them to say y equals. So we're going to make this say y equals. The way I'm going to do that is by solving for y. Meaning I'm going to add 1 to both sides so that the left-hand side becomes x plus 1 equal to 3y. Do we follow that step, inverse operations? How come I didn't actually add x and 1 and make it 2x? Yeah, they're not like terms. Can't do that. We just stick them next to each other. Okay. What do I do to get that y all the way by itself? What? Divide, yeah. Right now they're multiplied, so we do its inverse operation, which is divide. Now I don't need you to necessarily clean this up for this lesson. We can leave it as the big fancy fraction, or the big non-fancy fraction, I guess. Y equals x plus 1 over 3 is absolutely fine for me. Another way this might be written, now that it is an inverse though, is to switch that y for the inverse symbol that we used earlier. Basically putting back function notation instead of just having it as x or y equals. We like this. This is like nice finish of a math question. Now we don't need to restrict our domain because we have an HLT passing. If the HLT fails, that's when we have to do step 4, which means step 5 is just to check our work by looking at a graph. Now we're going to do this in an efficient way, which means what I want you to do is I want you to go to your calculator and I want you to type in the equation we solved. And once you get it in the calculator, you're not going to look at the graph. I want you to look at the table, because we want to get a certain number of values to put on our paper and check and see if it actually does reflect over that y equal x line. So I'm going to go to my calculator, and you will too, so grab your calculator. We're going to go to y equals, and we're going to type in fancy fraction, x plus 1 divided by 3. Literally just this. We're typing that in our calculator. In the graph, y equals. Now you can look at the graph itself, but that's not super helpful. What I want to do is look at the table. Now table is a blue word on top of graph, so how do I get to the table? Second and then graph. Now I'm not going to look at the ones that give me fractions. I'm just going to look for nice easy answers, nice easy coordinates. And I'm scrolling up and down. I see that on my graph or on my table itself, it says that there is a coordinate at -1, 0. So I'm going to put that down. I also see there's a nice pretty one at 2, 1. And then the next pretty one I see is at 5, 2. Now y'all know I'm real bad at drawing straight lines, so please forgive my straight line. Actually, not too bad. So here's why we do this. We should have a reflection, but not a reflection over the x-axis, not a reflection over the y-axis. We should have a reflection over this dashed line that we've drawn in for you. Do you see that these are flipped over that dashed line? We want that to happen. that shows us visually that these are inverse functions, that they flip over the y equals x axis. Do I have any last minute questions before we move on from this example? In this next example, what's the very, very first thing I did? Or in the last example, what's the very, very first thing I did? Check it with what? What is the test called that I'm using? HLT. Now, does this parabola pass the HLT? Does it? No. Oh, let's highlight it so you can see it better on your notes. We're talking about this parabola right here. If I look at that parabola, immediately, does it pass the HLT? No. We've got two places right here where it crosses at the same time. So that's a problem that we're going to have to address. So before we even get started, because the HLT was a fail, we have to restrict the domain. So what we do is we get to just ignore part of the graph. If we wanted this to pass, if we wanted the HLT to pass, I only want one side of the parabola to exist because I can't have both this side and this side at the same time. I can't have both this side and this side at the same time. I can't have this side and this side. So it's like one of them needs to go away, right? So watch what we're going to do. Feels weird that we can do this, but what you're going to do is you're going to take your pencil and you're going to mark out the graph until you get to the vertex. That's it. That's called restricting the domain. It looks a little weird because all we're doing is marking it off, and I've got a whole bunch of like markings on mine, so I'll try to clean it up a little bit. But if you look and ignore the part that we've scribbled out, does it now, the green part, pass the HLT? So what we did is we said we are only going to use the x values that are greater than or equal to 0, and then it will work. So when the HLT fails, which is going to happen for parabolas, you have to stop it at the vertex, in this case at 0, to be able to get it to have an inverse. Fabulous. Now, we got ahead of ourselves here, or in the notes, we went ahead and told you this. You probably politely ignored this. We already went and restricted the domain x greater than or equal to 0. Cool. That's because parabolas won't ever have inverse operations unless we restrict the domain. But now we need to find that actual equation. So when I'm going through the steps that are printed on the paper, what's the first thing I should change? F of x becomes y. So literally step 1 is just to change f of x to y. Second step is to do what? Switch the x and the y variable. Anywhere there was an x, now you put a y. Anywhere there was a y, now you put an x. But we don't like looking at equations that say x equals. We want them to say y equals. So I need to isolate y. How do I get y by itself? Square root both sides. If I square root both sides, I'm going to end up with square root of x equal to y. Well, that's exactly what I want. I want my equation to say y equal to something, and in this case, y equal to the square root of x. We could also write this with the fancy version as f inverse of x equal to square root of x. That's the fancy version. So again, this is why we had to learn this at the end of chapter 6, because when we wanted to find the inverse of parabolas, we had to understand radical equations. Now we're going to check our work again by just getting some coordinate points in our calculator and making sure it actually does flip over this diagonal line. So go to your calculator, go to y equals. We're going to just type in square root of x and get those points from the table. Yes, sir. Yes. the points that I get off of my table when I put that in, the cute ones, because I'm going to ignore the ones with all the fractions, I see that I have 0, 0. So there's one of them. The next cute number I see is 1, 1. The next cute number I see is 4, 2. Once you get about 3 points, that's enough to play connect the dots, and so we would connect the dots here. Does that purple one and the green one look like reflections over that diagonal line? Is the diagonal line in the middle of them? Good, we did it right. So you can always check in your calculator that they are inverse operations visually. So parabolas are weird because we have to restrict their domain. But it's okay because you literally just chop it in half. That's all you're ever going to do. Chop it in half, use the positive side. Let's go to our third example. Now they've already graphed this one for me. It's a radical equation. And we need to figure out what the inverse is. Does this pass the HLT? If I were to draw a bunch of horizontal lines, does it ever cross the green line more than once? No, so we're good. It passes the HLT, so I have this as my green line, and I know that my inverse is going to exist. So I go do some algebra to figure it out. First thing I do is I switch f of x with y so that we can have x's and y in my equation. What's the second thing that I do? We will hold on to that step, but before we do that, what do we need to switch? The x's and the y's. Very good. And now it's a radical equation that we learned how to solve earlier in this class. We would isolate the square root first, which means we are going to divide both sides by 2 to get those to cancel out. This would be x divided by 2 equal to the square root of y minus 3. And now what do I do with both sides to get that square root to go away? Square both sides. So when I square both sides, the square root and the square are going to cancel each other out. And we'd have x divided by 2 squared equal to y minus 3. Bless you. One last step to be finished. What is it? Ooh, not yet. We haven't isolated y. Add 3 to both sides. Very good. So when I add 3 to both sides, I'm going to have x over 2 squared plus 3 equal to y. And yes, I know we normally write them as y equals, but equals y is the same thing. So my fancy version of this is f inverse of x equal to x over 2 squared plus 3. Literally the same thing, just replacing the y with f inverse to indicate that they are inverse functions. Now, here's some things I would love for you to have noticed, or maybe not noticed until I point them out. What kind of equation is this if it has a square in it? A quadratic. Quadratics normally look like U's. If we were to draw a U on here somewhere, just do those look like direct flips of each other? Kind of. There's like extra in the purple, right? That's a problem. So we have to restrict our domain, again, in our inverse to make it make sense. Okay? In our inverses, we want to restrict the domain and or the range. For the green problem, it's really easy to notice its restriction of its range. What's the lowest this graph is going to go? That's going to be to the right, thinking up and down. How low does it go? Zero. So if y is greater than 0 in the green one, and we are switching all of the x's and y's to make the purple one, I should no longer write y is greater than or equal to 0. What should I write? Switch the x and y. X greater than or equal to 0. Which means that when I actually graph this, I'm going to cut off the parabola at 0. Let me do that again. So it looked like this. And if I say it can only be bigger than 0, I have to cut it off like that. Now do they look like they're flips of each other? This is why we always check our work visually. Because you may get something, you're like, wait a second, there's way too much going on here. That's when you restrict your domain or your range. Get it to cut off so that it actually looks like reflections of itself. Cool, cool, cool. We're going to let that be a sketch. So if you want to draw that in, we're not going to do it super accurately, but that way you can see what it looks like and that we had to restrict our domain. Now, one of the types of questions you may be asked in this unit is just to verify if two things are inverses. So what we have to do is solve one for its inverse. We don't have to graph it because we're just trying to see if it matches up with the equation that's also on the paper. So if these two are inverses, then when we solve the first equation for its inverse, it literally will just match up with that. Does that make sense? So it's just an algebraic problem here. The steps are exactly like they are on the other page, which means the first thing I do is replace f of x with y. And then I switch what two letters? X and y. And then I just solve back for y. Again, using inverse operations, what's the first thing I do in solving for y? Add 1 to both sides. X and 1 cannot be combined together, so I just write it as x plus 1. What's the last step here? What's the last step to get y by itself? Divide by 3. And when I do that, I get that the inverse, f inverse, would be equal to x plus 1 divided by 3. So does that actually match with what was written on the paper? Yes. So then we say, yes, they are inverses. If it does not match, number 1, we might go back and check our work just in case we did something silly. And number 2, we would say no, because they are not inverses. Now we're going to do number 5, but y'all are going to drive, which means I'm going to ask you to help me out the whole time. We're going to start with that top equation again, and we want to see if it matches the inverse of f of x, matches g of x. So Yuli, what's the first thing I do when I want to start this kind of problem? What do I replace? With what letter? Very good. So we're going to just replace all of f of x with y, just so we have x's and y's instead of f of x's and x's. Henry, what's the next step? It's something to do with the letters. So if we look in the example before this, right after we switched it with y, what did we do here? We just did this step. What? Yeah, very good. So we switched the location of x's and y's. Every y becomes an x, and every x becomes a y. Then all we have to do is resolve the equation so that it says y equals. So Lauren, if I want to get this by itself, because right now the y is cubed, which we will deal with later, how do I get rid of the 8? Very good. We divide both sides by 8. It'll get the 8 to go away, and we'll just have x divided by 8 on one side. And we just spent some time working on how to undo cubes. We did it on our Kahoot at the beginning of class. How do we undo a cube? Sort of. Not a square, though. Cube root. Very good. So what we're going to do on both sides is we're going to do the cube root of both sides, which will make the cube root and the cube cancel each other out. Which means we are left with f inverse of x, because all this cancels, right? And we just have a y left, equal to the cube root of x divided by 8. So my question for you, since we found this inverse, does it match with the question? No. So are these two things inverses? No. A third way that you can do these problems is by graphing them. And if you graph them and they don't look like they fold over a diagonal line, they're not going to be inverses. So that's one of the other things we could have done here, just to see like, whoa, these are not even close to looking like the same shape flipped over. So that's one way you can decide yes or no as well. Now, if anybody is in physics or will take physics, the next problem we're going to do is very, very helpful for like really complicated science problems. And in fact, a lot of your physics professors in college will have you do physics problems like this first before you do any of the physics. So physics is math in real life, it's whatever. So we're going to be finding inverses, which will help us find new formulas. It's called deriving a formula for different things. It's kind of confusing because, like this little hint box says right here, you're not actually going to switch x and y. We could do that in a very typical math problem because x and y don't really mean anything. They're just letters or placeholders. But in real-world situations, the x and the y, or the letters that we use, mean something. And we don't want to lose that meaning if we switch the variables. But the idea is still going to be the same of deriving a new formula. So number 6, it says, find the inverse of a function that represents the surface area of a sphere. So we have this formula here. We need that. Great. Then find the radius of a sphere that has a surface area of 100 pi feet squared. So the inverse of a function just literally means solve it for the opposite variable. So what we are going to do, instead of switching the S and the R, because we don't want to lose the importance of what those letters mean, what we're going to do is we're just going to solve this equation so that it says R equals. So that we have an equation that says the radius is blah da blah, instead of the surface area is blah da blah. This is helpful for physics because when you have ugly numbers, no offense numbers with tons of decimals, putting them into equations and solving with them is hard, but plugging them in and pressing go on a calculator, way easier. So to do this, remember we're trying to get R by itself. Right now, R is multiplied by 4 pi. Remember, pi is a number, so we're going to leave it as a number. We divide both sides by 4 pi so that our equation says S divided by 4 pi is equal to R squared. Now we're close to having this equation say R by itself. We're still doing inverse operations to find an inverse function. We just didn't switch the x and y again because it loses the quality of the letters. What do I have to do to get the squared to go away? Square root. So we're going to square root both sides, which will make the 2 and the square root cancel each other out. And all I have left is R equal to the square root of S divided by 4 pi. This is the inverse of surface area because I solved for the opposite variable. It's also called, in math, we call that deriving a formula, which is cool. We're deriving a formula. Now this question has two parts. The first part was to find this formula, check, we're done. The second part said to find the radius of a sphere that has a surface area of 100 pi feet squared. Now if we want to find a radius, and we have an equation here that says radius equals, all we have to do is plug the stuff in and press go on a calculator. So the radius for this question would be the square root of a surface area number, which is that 100 pi, divided by 4 pi. Now, obviously, we could do some of this in our head, but I know that mental math is not our strong suit, and I want to make sure you remember how to use pi in the calculator. So we are going to just do this in the calculator. Look at your calculator right now. Do you see pi anywhere on a button or above a button? Do we see it? What is it above? The little caret, the up caret for exponents, right? So when we type this in our calculator, we're going to make sure we use that button. So since we've put that in our calculator using the pi button, the calculator will calculate for us that the radius is 5. Now, if we had done this without deriving the formula first, without doing what we did over here, we would have to plug 100 pi in here and then solve for r, which just means there's more numbers floating around that we could accidentally round incorrectly. And in physics, that's like not going to fly, because if you lose your rounding accuracy, then the problem gets to be wrong. Okay, if you don't use the significant digits you need at some point, it's wrong. So if we wait to plug numbers in to the very end, you lessen your chances of messing up on the numbers themselves. Let's do one more example, last example for today. It says the distance in meters that a dropped object falls in t seconds on Earth is d equal to 4.9 t squared, where we want to solve the equation for t, meaning derive the formula for t or find the inverse, and then determine how long it takes an object to fall 50 meters. Now they gave me a distance, not a time, so I know I'm going to plug that number in for d. I just want to derive this formula so that we have a formula that talks about not d equals, but t equals. So what do I do first to get the t squared, eventually the t, by itself? Divide by 4.9 on both sides. These will cancel, and I'm left with d over 4.9 equal to t squared. Now again, I'm working on getting the inverse function, which means doing a bunch of inverse operations. What's the inverse of squaring something? Square root it. So we square root both sides to get the square to go away. And we would have that t, or my time that this object is falling, is going to be equal to the square root of the distance divided by 4.9. Again, this is helpful, especially when it comes to physics, if you had some ugly numbers you were plugging in for the distance. We don't want to solve with crazy decimals in our formulas. We'd rather solve with small little letters and then plug the numbers in later. But our question itself says, how long does it take an object to fall 50 meters? So to find that out, we would say, well, the time should be equal to the square root of the distance, 50 meters, divided by 4.9. So in your calculator, can you figure that out for me? There's no pi's in this one, so you don't have to use that pi button, but you do need a square root. And you're going to get an ugly decimal, and that's fine. We'll keep one decimal on this since our distance has got one decimal, or our formula has got one decimal. So we're going to use the squiggly equal signs to indicate that we rounded this number. And the time should be that it takes approximately 3.2 seconds for that object to fall 50 meters. Wow, meters. So again, inverse functions is just utilizing inverse operations on functions. to solve them for the different variables. In a plain x and y equation, you will switch the x and y and resolve for y. In a real world problem, you just solve for the opposite variable so that it says that variable equals. Now for today, there is not a big ideas homework assignment. There is a Desmos slides homework assignment. Do y'all know what I'm talking about with Desmos slides? Okay, it may not be linked on Google Classroom. I think I need to press go on it, but it will be there in 3 seconds once I press go.